Before we dive into section 4.5, which is about probability tree diagrams, we do need one tool from a branch of math called Combinatorics. Combinatorics, of which we'll explore quite a bit actually in this chapter. We can distill it down to the math of counting. And you might be thinking to yourself, well, that's how we learn math in the very first place, right? So that's where we start. We start with learning how to count from 1 to 10 and so on. What we really mean here, though, is when we have more complicated arrangements of things, not just, counting literally a set of a few things, but when we have drawn or selected things differently, as we'll see in some of these experiments, we need some basic principles that help us figure out the total number of combinations of arrangements or whatever we're examining. So for the sake of illustration, let's suppose we flip a coin 3 times. So our experiment, we're going to flip a coin, fair or not, it doesn't matter, 3 times. So this is an example of a multi-stage experiment because we can think of it as being carried out in 3 distinct stages. So we have stage 1, which is the first flip. We know we get either heads or tails. Stage 2, get the second flip, and again, we can get either heads or tails. And stage 3, we have our third flip. So this is pretty intuitive. This is not any different than what we would expect to happen. But then, how do we think about the final sample space? So the sample space is going to be the set of triples, or 3 tuples. So we can think of this as a triple, or sometimes we call this a 3 tuple. And each one is either a heads or a tails. Right? So how many possible, or what is the size of the sample space, right? For this, we need the multiplication counting principle. And there's a few different ways of writing this out, but we can suppose we have a set S composed of R tuples. R is a whole number. And so remember, a 3 tuple then would be a sequence of numbers where there's 3 numbers. A 4 tuple would be a sequence of 4 numbers, etc. And for each coordinate or spot or stage, we might call that the kth spot, there are n sub k possibilities. So in our example, for each one, right, we had 2 possibilities. So n sub k would be equal to 2. We'll go back to that. Then, the size of S would be n1 times n2 times ... times n r. Okay? So in terms of this example that we were talking about, so we have S is composed of all these different sequences of 3. So what we have here is we have 3 tuples, and for each spot, we have the same number of possibilities. 2, right? So this would be the same as if we were talking about true or false questions or yes or no questions, right? So there's 2 possibilities. It's binary. By the multiplication counting principle, MCT, then we know that there's 2 times 2 times 2, or 8 total possibilities. And we can write them all out. We could take the time to write out all the possible outcomes, which is all the different possible simple events. Sorry, I already wrote that one down. So first there's the event in which all of them are H, then 2 H's, of which there are 3, then the 2 T's, again there are 3 possibilities there, and lastly all 3 are T's, all 3 are tails, right? So that's the full sample space, and it took us, not that long to figure out the size of the sample space, but we can use this much more general and powerful examples. For instance, as an example, we suppose 4 chemistry books and 5 physics books sit on a shelf. How many ways can we pick one of each? We're going to suppose that they're all different. So we're looking at 2 tuples, because there's 2 categories here. Or 2 stages. Selecting a chem book and selecting a physics book. Call them E sub 1 and E sub 2, if you want. Where E sub 1 is the chosen chemistry book and E sub 2 is the chosen physics book. Then by the multiplication counting principle, there's one more thing here that we need. So N1 equals 4 and N2 equals 5. And by the multiplication counting principle now, so I write that down, MCT tells us that the total number of ways to select is going to be 4 times 5, or 20. And the reason why this is so helpful is because this ties into when we talk about probability tree diagrams, in that you can visualize the multiplication counting principle, for instance, the 3 coin flips, as you have a choice between heads and tails. And each time you branch out, again, and what you're actually looking at is the total sample space when you look at the total branching of the possibilities, right? So here's our stage 1, stage 2, and stage 3. And the multiplication counting principle tells us the number of distinct branches. So here's one, the HHH branch, which is all 3 landing on heads. Here's the THT branch, so tails followed by heads followed by tails. And each outcome has a distinct branch attached to it. Just like with so that was the first experiment we were looking at, and then there was the book selection experiment, in which we had, we could pick a chem book, right? So 4 ways to pick a chem book. Chem 1, Chem 2, Chem 3, Chem 4. And for each of those, we had 5 options for the physics book. And it can get really unmanageable really quickly. I'm just going to draw it right in one. Phys 1, Phys 2, Phys 3, Phys 4, Physics 5. Okay, so I'm not going to write out all of those, but you can see how the multiplication counting principle actually does give us something very helpful in that we don't have to write out all these different possibilities. We can just calculate it directly.